Okay, in this video what we're going to do is cover the last part of Chapter 9, which deals with the application of utility theory to the decision analysis process. Before we get started here, I'm going to actually get the pen all ready so I can annotate on the screen. So before we actually get into the utility piece, I want to just cover one particular aspect with respect to sensitivity analysis as applied to the go for broke problem. So we're continuing where we left off last time, and that was we were now considering the possibility of essentially purchasing additional information that'll give us sharper estimates in terms of whether or not there's oil or there's not. And so we introduced the concept of using the prior probabilities together with some conditional probabilities to create a set of posterior probabilities that then are conditional in that they describe what's the chance of oil given that you had a unfavorable or a favorable seismic study. So there's a section in here which talks about now applying sensitivity analysis to this now sort of more complex decision tree that involves prior and posterior probabilities and the whole bit. So the concept is still the same. In other words, for decision analysis, sensitivity analysis, what you're going to do is choose something that you're most uncertain about, and you're going to range that from low values to high values, and you're going to study what happens to your decision. Like, when does it flip from telling you to do one thing to telling you to do something else? Now, again, this is a multi-stage decision analysis problem, and what we mean by that is you have a decision now at time 0, which is whether or not to do the survey or not. And then after you get the results back from the survey, you have the second stage of decisions, which is whether or not then to drill or to sell the land. So this is just a screenshot. I'm going to show you the spreadsheet for this here in just a second. But I'll point out just kind of a couple of notable things here. First of all, down here on the lower right, they have incorporated the template for computing posterior probabilities like right onto the same worksheet. You've got named ranges up here defined. Again, that convention of using the light blue to always illustrate something that has been provided to you in terms of data. So this is where you're able to declare all of your input parameters. And then these the little yellow sort of tree right here is basically, I'll show you the logic behind that, but it's basically just, it's going to report a yes or a no depending on what's happening at that time 0 decision, which is right here. And it's going to declare a drill or no drill depending on the decisions, if it's unfavorable or if it's favorable. Okay, so again, there's nothing really fancy here. It's just a way of sort of very nicely consolidating for the user the key decisions that you're trying to address. Now, so let me just shell out here to the spreadsheet, and I'm going to discard it. So we'll go to the full go for broke. And so here's the tree. Now, I will point out one thing. I think they use, when they use the Risk Solver platform for Excel, I think they use a particular function that's created in that macro. For me, it was giving a name error on the column AD, and it was giving a name error on the cell V26. And all you got to do is recognize that what you're looking for in this expected profit cell, which is V26, is equal to the value that is reported at cell A30. So you can do that by renaming A30 to be the expected profit, or expected payoff actually is the name of that range. But nevertheless, just make sure that this value here, V26, is equal to A30. So, because A30 is automatically created by the tree generation, whether that's using Risk Solver or using Tree Plan, either one, this value has a function assigned to it. So for this particular example, again, what we've had to do is key on a couple of things. One is the sort of variable of interest we're most focusing on here is this prior probability of oil. And you notice that's the input right here at V9. And so what we're going to do is we're going to say, hey, that's the one we're most worried about. The true probability of there really being oil on the land. And we had an estimate early on of 0.25 or 25% chance of that, but we want to see how sensitive our overall decision is to that particular value. Now again, this is more complicated because we've got the possibility of purchasing the survey study, which will sharpen our estimates. But nevertheless, this is the variable we're going to range. So as we construct our data table here, we would identify what is the values that we want to test, and then we would specify in that decision tree that we want to put those values right here in cell V9. So when you're declaring that data table, you've identified what the outputs are. You're interested in this case, V15, which is the decision in terms of should you do the survey or not. You're interested in these other two decisions. If it's if you don't do the survey, and if the survey comes back, or if you do the survey and it comes back favorable, if you do the survey and it comes back unfavorable, and then finally, if in fact if there's no survey, what you do. So. And then, of course, the reported expected payoff, which is this, again, it's this named range called expected payoff, which is reflective of what's being reported in cell A30. So, for example, if I put in 0.3 here, probability of finding oil, you'll notice that, the data table adjusted and everything like that. You'll notice that, in fact, it's reporting an optimal expected payoff of 143.2 thousand, and it is giving you now the appropriate decisions depending on whether it's saying now you should do the survey, and if it's if you do the survey, then what to do in terms of drilling or selling depending on what the outcome is of the survey. So we'll set it back to 0.25, and again, this is just a classic kind of all-in-one place sensitivity model now. And what's interesting is if you look at the results here, so now as we've ranged it from probability from 0 to 1 as far as the true value of there being oil on the land, you'll notice some very interesting stuff. In other words, like if the prior probability of there being oil on the land is super low, it says like, don't do the survey, but go ahead and drill. And it tends to kind of follow that pattern, except there's this sort of sweet spot in the middle at a probability of 20% or 30%, where it does suggest you will benefit more from the additional information than you will if you don't get the additional information. So in other words, there's only this sort of narrow range where it says it really makes sense based on the cost of the survey and the added information that it provides, that the optimal solution at time 0 is to actually do the survey. And then it also, if you look at this, it very much depends on what the results of that survey come back as. So clearly, if the survey is favorable, it says definitely drill. But if it's if it comes back unfavorable, then it says you should in fact sell. And so again, this is just kind of interesting. And the interesting thing about a strategy is where you're declaring the decisions at any point in the decision tree where you might have to face decisions. And so in this way, you've got sort of a complete set of actions in terms of to guide your decision making in the event, a prior probability of finding oil is given. So again, this is, let's go back to the slides here and just kind of summarize what we have. And I think I've lost my pen here, so let me bring that back up. So so again, this is the reported values, and as you can see, again, one other thing to notice is this column on the right here is, you know, the higher the prior probability of oil, meaning the probability of there truly being oil on the land, the higher that is, you can see, you know, how profoundly, you know, highly sloped the payoff is. In other words, you know, it's 90, 90, and then 102, and then it really starts to shoot up pretty significantly for you. I mean, for every 10% increase in chance, it's going up by about $80,000. So clearly, it's, you know, this prior probability of oil is super important in terms of the eventual, you know, expected payoff from this venture. And again, what this boils down to is, you know, it turns out the optimal policy here is, you know, if the probability is less than about 17%, it says just go ahead and sell the land. If the probability is between 17 and 31%, then it says do the survey. And that's when you're going to actually benefit from the added information more than the value of the cost of the survey. And of course, then drill if favorable and sell if not. This is what we're arriving at. And then if you get over 31% probability, then it says don't bother spending the $30,000 for the seismic survey. Just go for it. You know, spend the $100,000 and drill for the oil. So very, you know, this is in some ways it seems very complicated, but in the grand scheme of things, this is a pretty simple problem that, you know, in compared to what you could face in terms of other multi-stage kinds of decisions. Now, so we're going to transition this notion. We talked about it in class today. We said, you know, like, you know, what would you pay to bet on that coin flip? And what was clearly apparent is a couple things. One is not everybody was making decisions with respect to expected payoff. I mean, if that was the case, everyone would have paid up to, you know, exactly $50 to play that coin flip for $100. So, so people are different from one to the next in terms of their feelings about risk. And another key kind of component is that people's kind of feelings about risk change depending on the size of the money. And so all of a sudden, the people that were willing to pay $50 for a 0-100 coin flip, all of a sudden when it was, you know, $0 to $10,000, they weren't willing to pay $5,000. They maybe only would pay $2,000 or something like that. So that's the two key things. People differ from one to the other, and the other is it sort of the attitude changes as the dollar values get higher. So again, it's kind of a sobering result because it's like, wow, not everybody makes, you know, we've been working on all this expected payoff and stuff, you know, modeling the trees in this fashion, and it turns out that not everybody makes decisions in that way. So so, you know, however, like you said, we kind of witnessed this in class. If I gave you a 50-50 chance of winning $100,000, you know, what would be the certain amount at which point you would be indifferent between the coin flip for $100,000 or the certain amount? And again, whenever that's different, that means you've got sort of utilities that are at play here. So again, most people would pick the $40,000, even though you're giving up $10,000 of premium to avoid that risk. And that's why we call it risk aversion, by the way, because you're avoiding that risk. So this whole notion of a utility function is a way to map money into sort of happiness with respect to a given decision maker. So again, it's transforming money to an appropriate scale that reflects their preferences. So this is what a typical utility function for money may look like for someone who is somewhat risk averse. Now, what this means is the following. First of all, the utility scale on the y-axis is ranging from, you notice, from 0 up to 1 for this particular little example here. The money values are ranging from 0 up to 100,000. But you'll notice it's not linear. if it was like linear, you'd have this perfect straight line. That's not a very good straight line, but it'd be a perfect straight line between the lower left and the upper right kind of corners of this square. But instead, it's sort of bowed out a little bit from that. Well, a perfect straight line between those corners would be reflective of risk neutral. But in this case, you're a little bit bowed out, which suggests you're risk averse. And here's one way to think about that. And let me clear the ink here for a second. So one way to think about this is that if you went from 0 to 30,000, check it out. Your happiness went up this far right here. Like, that's a pretty big jump. As we went from 0 to 30,000, our happiness jumped up that much. Now, here's the interesting part. If we were to get now a second $30,000, it's like, like someone gives you that $30,000, you're like, oh wow, this has made me really happy. Then someone gives you a second $30,000. Well, here's the point. The incremental gain in happiness for the second $30,000 is only only this much. So if you compare the sort of the arrow on the left to the arrow on the right, you'll notice that that second $30,000 really didn't bring proportionally the amount of happiness that the first $30,000 did. And again, this is a tendency that we have is typically, again, most of the population exhibits some degree of risk aversion. Now, what differs, if we're all risk averse, then what differs is sort of how dramatically this curve would bow like that. Like, for example, if the first $30,000 brought you this much happiness and the second one only raised it a little bit more, then that means you're extremely risk averse. And, like in the little in-class things, for that coin flip for $100, you may only risk like $5. Okay? So, and we talked about that as the gap between there, you're really sort of foregoing a lot of expected payoff in order to avoid that risk. So again, this is sort of the idea behind it. And again, like we said, you can be risk averse, and that's typical over here on the left. You could be risk seeking, and risk seeking, I mean, think about this. Guy goes to a casino, he wins like $1,000, and it just brought him a whole lot of happiness right to there. So this is the first $1,000 from here to here. But a pathological, compulsive gambler would say, oh my gosh, I won $1,000, big deal. I really want to win $2,000. And that's why they then they're going to get, check it out, if we go out now another $1,000, it's got this increasing amount of happiness that comes to that individual. So again, you're comparing the height of the happiness brought on by the first 1,000 to the incremental gain as we went from the first 1,000 to the second 1,000, and it's much higher. So they only get like they need a big buzz, they need to strike it really big. And of course, the risk neutral, the first 1,000 raises you that much, the second 1,000 basically raises you an identical amount. So you're just as happy with the second 1,000 as you are with the first 1,000. So when a utility function for money is incorporated into a decision analysis approach, it must be constructed to fit the current preferences and values of the decision maker. And again, these are very individual for a person as well as for an organization. Now, there's one fundamental property as we apply these utility functions, and that is the following, is that under the assumptions of utility theory, the decision maker's utility function for money has a property that the decision maker is indifferent between two alternatives if the two alternatives have the same expected utility. So what this all means is, at the end of the day, instead of a tree that has a bunch of financial values put on it, instead it's going to have a bunch of utility values put on it. And what you're going to try to do is maximize the expected utility. So again, everything applies in terms of Bayes' decision rule and calculating, the expected payoffs, but instead we're going to be calculating expected utilities is what it means. So again, the optimal decision is one that maximizes now the expected utility. So, like for example, in this top one says, you've got a 25% chance of getting $100,000. So imagine someone is saying, wow, you either get a 25% chance, like a wheel spin with a 25% chance of winning $100,000, or a sure $10,000. So this would imply, so this person's utility function would be consistent with that, because a probability 1 of getting 0.25 is equal to a probability of 0.25 of getting a utility of 1. So those are their expected utility is equal. A certain 0.25 or a 25% chance of a utility of 1. And I mean, here's another example here. A 50% chance of $100,000 is equivalent to, or you're indifferent between that and a $30,000 for sure. So again, we're now saying, well, you get a certain $30,000 that carries with it a utility value of 0.5, or you've got a 50-50 chance of getting the $100,000. So you've got a 50-50 chance of getting the utility of 1, which has an expected utility then of 0.5. So what this is pointing out is, with this particular curve that I'm showing you here, you've got these kind of sort of points of comparison and difference, basically. So the way you do this is the following. So like if you're considering a situation like in the Gopher Broke, where they can make as much as $700,000 or they can lose as much as $130,000 if they do a survey and drill. Those are sort of the endpoints. Those are the sort of maximum and minimum values of the cash flow that we're concerned about for this problem. So what you do is you would assign a utility of 1 to the maximum value. So the utility would be that, that positive $700,000 that you could potentially get. That's the most net cash flow you could get. And you assign the utility value of 0 to the minimum, which is, in this case, it's a minus 130,000. And so then what you do is you say, okay, so that gives us kind of 2 points. It gives you the 2 endpoints of the utility curve. But now what you need to do is you need to kind of figure out how much that curve bends. So you need a few other points on there. So what you do is you say, look, okay, if I'm given the choice, someone says, hey, we're going to do kind of a quasi coin flip, where you've got a potential of $700,000 of winning, and you've got a $130,000 of losing. So at what probability would you sort of assign such that you would be indifferent between some other potential payoff in that option? So the example that they gave was, they said, well, you've got the sell value, which is you get a $90,000 if you sell it. So they kind of said, well, so what would have to be the probability of getting the maximum payoff such that you'd be indifferent between taking the gamble of either getting the maximum or minimum payoff or getting the certain payoff of this other value, which in that case was $90,000. Well, they kind of worked that through in the problem, and in the problem that sort of other value that they were looking at was, again, selling the land at a certain $90,000. And what they came up with was that the associated probability, and this is U of, I need to get a pen, by the way. So that's U of $90,000. Turns out they said that was equal to 1/3, or at least a better mouse here. I'm doing this on one of those touch pads. So that's what they determined just in the narrative within the chapter. So what they did was they started by setting the minus, that's a minus 130. They set that equal to 0. They set the 700,000 equal to 1, and then they determined that this was about 1/3. So that's now 3 points that are defining this curve. So you've got the 0, you've got the 1, and now you've got, you're saying, okay, well, at $90,000, you've got an associated probability here of, say, 0.33. Not very good. I realize that. There we go. So what you do is you start, with the 2 endpoints, then you pick a value in the middle, and then you sort of query your way to the appropriate probability, and that helps you define that. And so this is exactly what they did for the 90,000, and that's how they associated, a probability of 1/3 with that. Now, you can then use that, and you can test all these other values to basically come up with, that was just one mapping of the point of the 1/3, which is right about here. But you can do that for all of the other values that were given. There was 60,000, there was 670,000, etc. In other words, all possible net cash flow values that we had characterizing this problem. I mean, they were all these ones right here. So anyway, once you do that, then now you have, again, a mapping of the utility from the associated dollar values. And so, again, this is just, we're going from here to here, is the resulting utility values for, this is the mapping of the utility value corresponding to each dollar payoff value. Then that's what you put into your tree. So if you look up here, we don't have the, right down here where it's a 1, that's the case where you didn't do the survey, you drilled, and then you found oil, and you get the $700,000. So this is the point where you're equivalent to the 700,000. Oh man, I'm telling you, I've not been drinking or anything. This is just like tough on the touchpad here. This one up here, let me see if I can do this one. There's something wrong with the touchpad tonight. Is $670,000 because you paid $30,000 for the survey, and then it came up unfavorable, and you went ahead and drilled, and you ended up hitting the oil. So you'll notice all these values in here. This is that sell it for $60,000 because you did pay money to get the survey done. Here's selling it for $90,000 because you didn't pay to get the survey done, etc. So again, what you're doing all along the way here is you're putting in these you're putting in the associated whatchamacallits, the associated utility values in each case along the way. So anyway, so that's how you do it, and then what you're getting at there, and let me go back to the, we'll say discard. So let me go back to a tree here. So again, this is sort of the same tree we saw before. That's all set up with respect to the data table for sensitivity analysis, but you'll notice that it indeed has these resulting, it's got these, it's got the utility values in here instead of the dollar values, basically. So you're putting in the utility values in each of these cases. And it's set up as before, and again, what happens is it does change a little bit in terms of, now that you're considering risk here, you do have actually just now one case out of the 10 where it says for you to do the survey, and it actually suggests sort of a little more selling than drilling in this case, because this guy Max, he is sort of, he's risk averse, but kind of only slightly risk averse. He realizes not the end of the day if he loses $130,000. So anyway, that's sort of the introduction of of utilities. I don't want you to get too hung up in it, but I do want you to be able to, if you were presented with, if you were presented with utility values and so forth, you would know how to evaluate them within a given tree, where you're now shifting to maximizing, say, expected utility in this case. So with that, we're going to sign off. That kind of finishes our material here for Chapter 9. Now we're going to do some stuff in class to talk about psychological biases and heuristics, which get in the way of us thinking clearly a lot of times with respect to decision making. And so we'll do that live in class. So thanks for listening, and we'll see you back in class. Take care.